So I'm going to jump down here in StatKey to the normal section under theoretical distributions. So we're moving away for a moment from the randomization simulations, and we're going to take a look at some theory for a little bit, and then we'll come back to the randomizations to see how they compare. So a normal distribution is this bell-shaped curve, and we've seen this over and over again in the sampling distributions that we've been playing with. The one we're looking at right now has a mean of 0. You can see that here on the right and here at the bottom, and a standard deviation of 1. So if I take a look at, let's say, a two-tail plot, and I look at one standard deviation on each side, I can see that about 68.3% lives in the middle here, and I get about almost 60% in each tail for probability. So a situation that this might be more relevant to help us understand it would be looking at human body temperature. So let's go with the default assumption that average human body temperature is 98.6. Standard deviation tends to be about 0.7 degrees Fahrenheit. Now, if I look at a standard deviation to each side of the mean, I'm going to look at the two-tail test here. If I go one standard deviation to the right, that would be 98.6 plus 0.7, which would be 99.3. And because I picked a two-tail test, it's going to give me one standard deviation to the right of center and one standard deviation to the left of center. And here again, the mean is my center, 98.6. And you can see I get the exact same values I was getting from that, what I call the standard normal. Standard normal, again, is when the mean is 0 and the standard deviation is 1. So the standard normal is what I talked about indirectly way back in chapter 2 when I was talking about measuring things using standard deviations. And the number of standard deviations something is from center, that's called a z-score. So anytime I jump, say, one standard deviation to the right of mean, that's one z-score to the right. Two z-scores to the right would be another 0.7 in this case, which would be one standard deviation. So we check that out. So if I take, let's see, 98.6 plus 0.7 plus another 0.7, that's going to give me 100 on the right. And this is going to automatically calculate the left side for me too, which is kind of nice. So, because I picked two-tail. So here I get about 95% in the middle, and so that's two standard deviations to the right, two standard deviations to the left. So what I should find is that if 98.6 is average human body temperature, and I go out and measure the temperature of a whole bunch of people, let's say I did 100, it was a good random sample, I would expect 95% of the people I sampled to have a body temperature between 97.2 and 100 degrees if they're a normal, healthy adult, right? And it's a good random sample. Now, is everything that we measure normally distributed? The answer is no, it's not. However, sampling distributions, right? The idea of a distribution of a whole bunch of different samples of the same kind of thing. Excuse me, go away. They tend, sampling distributions for means and proportions, they will be normally distributed. And we'll get to that later this week as to why. But it's pretty easy to work with. So suppose you wanted to know, let's say switch to a right tail test, and reset it, right tail, go back and hit the parameters, 98.6, 0.7, okay. So if I think an adult is healthy, you know, what's the probability they have a temperature above, let's say 101. So here the probability is, let's see, 0.0003. So if we multiply that by 100, puts the decimal point right there, we get 0.03%. So 0.03 of a percent chance of finding a healthy adult with a body temperature of 101 degrees. So that indicates that they're probably not a healthy adult, okay? Because the chance of finding somebody with that temperature is so remote. Okay? So it's a very slim chance. So that's how we say, hey, somebody's probably sick. So there are good reasons to look at the distribution of certain measurements, and body temperature is a great one. So again, this is the normal distribution calculator, and you can do left tail tests and right tail tests, and you can either plug in a number that you're interested in, like in this case, if I type 97, what percent of people would have body temperatures that are 97 degrees Fahrenheit or less? I would expect about 1.1% of people to have that. Suppose I wanted to know what temperature will about 5% or less people have. And so it turns out 97.45 roughly, having a temperature of that or lower, only about 5% of the population should have a temperature of that or lower. And the lower we go here, the more remote a possibility is. What percent of the population should have a body temperature of 98.5 or smaller? About 44% of the population should have a body temperature of 98.5. So there's all kinds of questions we can answer. And we can answer a question based on probability. Like suppose I wanted to know the median, enter 0.5 for the 50th percentile, 98.6. Suppose what I wanted to know what the 60th percentile is. So I enter 0.6 for 60%, and I get 98.777 is the 60th percentile for human body temperature. So again, I can answer questions about probability. I can answer questions about body temperature and probability, all with a normal distribution. Again, keep in mind, not every single distribution of numbers we collect is normally distributed, but some are. And it turns out there's a more important reason for looking at the normal distribution, which we're going to get to in the second half of this week. So have fun using this normal distribution calculator. Figure out how to exit. There we go.